everyone, and welcome to Physics for Dummies Part 2. Now, excuse me if I do sound a little bit different, that is because I'm sick. But let's just get right into it with a little bit of recall from our previous lesson. So, we talked about Newton's first law of motion, which stated if there's no force acting on an object, then it's not going to move. So let's say we have a ball, and the ball is just on the floor, pretend it's touching. Alright, this is also how we draw the floor in physics with these lines. So let's just say this is like grass and this is a soccer ball. It's not going to move unless someone kicks it or pushes it or picks it up. Therefore, no external force acting on it, it's not going to move. Let's draw its FBD. So over here, we have the ball, right? The force of gravity acting downwards. So we're going to label that as FG. And then we have the force, the normal force acting upwards, and we're going to label that F. And now, remember, force of gravity is just the gravitational pull of the earth pulling things into the ground. And the normal force is what's stopping gravity from pulling us through the ground. Normal force opposes gravity. Now there's different types of forces. It's not just these two, but we're gonna talk about those in, I think, part 4 or part 3. I'm not too sure yet. Anyway, let's get into this lesson now. So now we're going to talk about Newton's second law of motion, the law of acceleration. So Newton states that the harder you push an object, the faster it moves. And heavier objects need more push to move. So in mathematical form, it means sigma F with a vector sign equals m times a with a vector sign. So the sum of all forces acting on an object is equal to its mass times its acceleration. And these arrows are vectors. I'll get into what vectors mean soon enough. So let's talk about it. So force is measured in newtons, named after Isaac Newton himself. Mass has to be in kilograms, and acceleration has to be in meters per second, or meters per second squared. Now, what that means is basically, if you know how cars, right, on their gauge, it says kilometers per hour, let's say, or miles per hour. So it's just telling you how many kilometers you're going to go in the span of 1 hour. It's the same with meters per second, right? Meters per second just means how many meters you're going to go in 1 second. But meters per second squared means it basically means for every second of travel, you gain speed. All right. So if your car is accelerating at, let's say, 2 meters per second, right? Every second you gain an extra 2 meters of speed. So let's say, when your car is at 0 seconds, your acceleration is equal to 0 as well. When you're at 1 second, it's equal to 2 meters per second. Well, your speed is equal to 2 meters per second. I should probably clarify that. Well, we'll just label that as V. Now, after 2 seconds, your speed is going to be 4 meters per second, because for every second of travel, you gain 2 meters per second of speed. So at 3 seconds, it's going to be 6 meters per second. That's your speed, right? And so on and so forth. Every second, you're going to keep adding on 2 meters per second, right? That's what acceleration is. You're basically getting faster and faster and faster. Whereas with speed or velocity, you're staying the same. You're going at the exact same speed. All right, let's get back to this. Of course, mass is in kilograms, acceleration is in meters per second squared. And keep in mind, acceleration happens in the direction of the net force, or the force is acting in the direction of acceleration. This law is actually one of the most important ones because it explains how objects move in the real world, and it's used in all sorts of different aspects in life: engineering, sports, and space exploration. It's how we explain how the world around us functions, right? So let's get into what these little arrows mean. So a vector is just a quantity that has both magnitude and direction. So, acceleration, all right, I like to draw it like this. Remember, excuse the poor handwriting. Let's say acceleration equals 2 meters per second, right? And then we also need to meters per second squared. We need to specify what direction it's going, right? So let's just say north. All right. This means this quantity is pointing, northwards, right? Your acceleration is going north, up towards the top of the page or the top of my screen. And scalars are they only have magnitude, mass. Let's say 5 kilograms. There's no direction. It just has magnitude, only has size, right? Another example would be a force 10 newtons to the right. Basically, vectors are essential in physics to describe motion and forces and more. Now let's get into an actual example of applying Newton's second law of motion and using this equation. Alright, this is one of the most important ones. So over here, we have little Timmy who dropped a ball, alright? Now, the mass of the ball, hypothetically, let's just say it's 1 kilogram, and the gravitational acceleration this is not hypothetical, by the way, this is what it actually is. It's around 9.81 meters per second squared, okay? Now, in this example, we're going to ignore drag or air resistance, right? If you guys even know what that means, but yeah, just ignore air resistance for now, ignore friction. We'll talk about that later. So we know that the sum of all forces acting on an object is equal to its mass multiplied by its acceleration, right? Oh, also, don't forget that in equations like this, you want to specify what direction you want to make positive. That's the whole reason why we even have vectors, right? So in here, the only force acting, the thing making the ball fall down is gravity. So if it's falling down, it makes sense that we're going to make the down direction positive, right? Now, if you were throwing a ball up into the air, right, and it was accelerating upwards, then we would make the up direction positive. So anyway, we know that let's draw its FBD first, alright? I should have done that. Anyway, the ball, and here's its FBD. There's only gravity acting on this object. FG. Remember, vector sign because it has direction. Now, we know that FG, we can drop the vector sign and just write a positive here, because remember, down and down is positive, is equal to its mass, right, times the acceleration, which is also going to be positive because it's accelerating downwards. Positive A. I like to write things like this because then it eliminates the need to have to add direction later on. So this just simplifies the whole process a lot. So Fg is just going to be equal to 1 kilogram, which is the mass of the ball, multiplied by the acceleration, which is 9.81 meters per second squared. Now, if we calculate this, it's just going to give us 9.81 newtons. So the force of gravity is equal to 9.81 newtons downward. Well, this is just the magnitude, right? If we want to write it properly, right, we have to do the vector sign. We have to say 9.81 newtons down. We need to specify its direction if we want to write it as a vector. See, because the ball is falling down, right, the force of gravity is pointing downwards. That's why we say Fg is equal to 9.81 newtons down. Anyway, that was pretty much everything for today, right? Keep in mind that you always need to use vectors to be fair, vectors aren't too important if it's a simple calculation like this, where it's just one force acting on it, but soon enough we're going to talk about more complicated forces, or more complicated systems, right, where forces are pointing in different directions, and we're going to need vectors to calculate that, alright? Because if you don't use vectors, then the magnitude it gives you is actually going to be wrong, right? Like, for example, let's say if you did throw the ball upward, then you would be like, oh, well, here's FG, and then here's the applied force. Now, an applied force is just a force that you yourself apply, right? So if you throw the ball, you apply the force on it, making it go up, but the force of gravity is still acting, right? Now, if you said you have to decide which one to make positive, it makes sense to make the up direction positive in this case because it's accelerating upwards, right? It doesn't make sense to make the force of gravity positive because, well, the ball is not accelerating downwards, it's accelerating upwards, it's going up. So that's why you would say up is positive, and then you would write sigma F equals ma, right? So you made the up direction positive to account for vectors. So then you would be like, well, FA is positive, right? But then, wait, if FA is positive because it's pointing up, then what is FG? Well, FG is negative, all right? So that would equal its mass times acceleration. Now, acceleration is still positive because, well, FA is bigger than FG, meaning it's accelerating upwards, right? So that, therefore, FA minus FG equals m times a. And if you wanted to calculate the net acceleration, you would just divide both sides by m to give FA minus FG over m equals the acceleration, right? Well, the acceleration magnitude as a scalar. Although if you want to write it in vector, you would just say up. You would, add the vector sign, then you would write up depending on its value because it's accelerating upwards. Another thing, all right, here's a new diagram that I like to use. If you know for a fact where it's accelerating, or this basically helps you, right? You just draw a mass acceleration diagram. So you label this as the m, and then you'll draw the acceleration. Okay, so this shows us that if the mass, right, if the question says the ball is going upwards, then the acceleration should also be pointing upwards. So it'll help you draw the FBD. If you know the acceleration is upwards, you're going to make FA bigger because FA is bigger than FG. FA is what's making the ball go upwards. Anyway, yeah, sorry for that side tangent, but yeah, that was Newton's second law, the law of acceleration, one of the most important ones, sigma F equals ma. All right. Anyway, thank you for listening to me rambling on.